All right. Our next talk before lunch is from Xiaocheng about parallelizing the main thread. Xiaocheng, please go ahead.
Hi everyone, my name is Xiaocheng. So I was on the Chrome rendering team until January this year, so now I'm at Huawei. But you can still reach me via this email and also on Chrome and Slack. So today's topic is about parallelizing the main thread. So first of all, some disclaimers. So this is not an official project of any kind because it's not even a Google project and nothing is guaranteed to land. So it's more for discussion purposes. So this is not a completely new idea. So a few years ago, Stefan proposed made a talk on generational DOM, which is also about parallelizing the main thread. So the main idea is the same, but so first it's discovered independently. So I didn't talk to him until a few days ago that I learned, okay, he made this talk. And there are some different technical choices which actually lead to some different performance characteristics. And I believe this version actually leads to a higher level of parallelism. And also some interesting use cases. And the Stefan's talk was quite technical, and this talk will be less technical. It's more about implications and also, yeah. So in a word, it's going to be wilder. So what is it about? So one of the first things I learned after I joined the Chrome team was JavaScript is the main source of strength. So how about making it parallel? So the main purpose is to make JavaScript and layout run in parallel, but it's actually we can achieve more than that. So yeah. So let's go to the overall design. So first, let's make an abstraction of what's going on the main thread. So the main thread. The abstraction is there are two kinds of tasks currently running on the main thread. So one is business logic, which we consider as mutators to the page state. And what the page state is basically the DOM plus some other data. And another type of tasks is rendering. So rendering is triggered by begin mainframe signals, which is about like 60 times a second. And what it does is it reads the page state, again, which is mostly DOM, reads the page state and does a bunch of calculations and then pushes the output to a backend, which is currently ECC. So, and again, this is an oversimplified abstraction because there's a lot of other things going on, but this, for now, it works. And how do we parallelize it? So we split the main thread into two threads, so a business thread and a render thread. So the business thread is for running business logic, so which is like the business thread is the thread that can mutate the page state. And another thread is the render thread, which periodically reads the page state and does all the calculations like layout and style layout panes, and then pushes the output to CC. And obviously there will be synchronization between the two threads. And so the first part is how does it read the page state? So it doesn't need to read the up-to-date page state. It reads a previous snapshot, and then it does the calculation based on that snapshot. And while the calculation is going on, the business thread can keep working. And another part is about UI event, because there will be some business logic that depends on the rendering output, for example, hit testing. So here, UI events, for example, mouse clicks will be triggered on the render thread first and to perform hit test there because that's where the rendering output resides. So we do hit testing there without blocking the main thread. And then if there's any need to pass it to the main thread or business thread, we post a test there. So this is the overall design. And as you can see, the critical part of this design is the snapshot. So because if we do it in the naive way, there will be significant blocking between the two sets. And here the goal is to reduce the blocking as much as possible. And ideally, I want it to be there should be no blocking at all. So yeah, so before going to what I'm about to propose here, here are some common approaches, or I call it naive approaches. So the first one is we pass the snapshot with a message. So it's like how we synchronize between the main thread and the JavaScript worker thread. And the messaging is the timeline is like this. So whenever we need to do rendering, we need to first ask the business thread to create a snapshot, and then send it to the rendering thread via message, and then it keeps working. And as you can see, this prepare snapshot phase is blocking, which we don't like. And another idea is like we use shared memory, but we duplicate the page state on both threads. So when the rendering thread receives a begin mainframe signal, it passes it to the business thread and asks it to update the snapshot on the rendering thread. And then after the update, both threads can keep going. So this is actually the model between the how currently the main thread and the CC thread work, because currently the two threads are maintaining a duplicate of the paint property trees. So but again, there can be the blocking may be smaller, but there's still a global blocking which we don't like. So here, what I'm about to propose is called persistent data structures, which is something I learned from academy. But so there's a rich literature in the academy, but not much in the industry, and it's just most applications are in functional programming languages. So the basic idea of a persistent data structure is it's a data structure that can be mutated without destroying its history. So we can mutate it while preserving the history, and we can query the history with a version number. So yeah, so it's a immutable data structure of some kind, which is perfect for parallelization. And the persistent techniques are mostly two techniques. So first, the fundamental thing is, of course, copy on write. But there are two more techniques to make it globally persistent. So the first one is path copy, which is what we are doing a lot currently. So let's say if we want to mutate a node, we track all of its in pointers and copy the entire path. And we're very familiar with that, and we know that it doesn't work when the data structure contains cycles, because in which case you have to copy the entire data structure. And another approach is called a fat node, which is we make a node fat by storing multiple version snapshot in it. So for example, here I mutate that purple node, and then I put both versions in the same fat node. And the links now should point to fat nodes instead of the version snapshots. So in this case, by maintaining multiple versions in the fat node, we can keep the entire history. And also in the literature, there are techniques that combine both of these and achieve some very amazing performance complexities. But we won't go that deep, because we don't need that. So here, for our scenario, a very basic observation is we only need to maintain 3 recent versions. So the first one is the latest version, which is what the business logic is currently working on. So And the second version is the latest unrendered version, which is what will be passed to the next rendering cycle. And the last one is the latest rendered version. So we only need to keep 3 versions. And since there are only 3 versions, we don't need that path copy technique, but we just go to the fat node technique completely, because we just need to maintain at most 3 versions in each node. And with this technique, we don't need any global lock. So the blocking only happens at a very primitive level when we're hitting atomic pointers. And memory overhead is so since we need to maintain 3 versions of every node, so in the worst case it's 3 times, but it's achieved only if the updates are very bad. It is spread out all of the DOM tree, and it keeps going and going and going. But so in most cases, there should be some hot region inside the DOM tree where we reach the worst case, and at other parts of the DOM tree, we just need to maintain 1 version because there shouldn't be any more updates going on. And finally, if the page stabilizes, and we don't need to keep any historical version, so in the end, it will to converge to just 1 time. So at Huawei, we made a minimal demo. We implemented a minimal demo that contains a persistent DOM tree with fat nodes. And also, there are 2 threads running. So a business thread that keeps mutating the DOM tree, and also a rendering thread that keeps performing not exactly rendering, but 2 types of tests. One is heat testing to simulate the UI events, and another one is rendering test which is not really rendering, but just traversing the DOM tree. So, and the 2 threads do not block each other at all. And once again, except when hitting the same atomic. So if you think about it, so we have 1 thread that keeps mutating the DOM, and another thread that keeps traversing the DOM. Is not very different from running JavaScript and layout in parallel, except some tiny technical issues. Yeah. And also, we have some homegrown concurrency verification tools that, so we verify the demo with the concurrency, with the verification tools, and seems to be correct. Yeah. But in the end, one last thing is it's currently based on atomic share pointers, not RLPAN, because RLPAN currently doesn't quite support this kind of concurrency, which we will talk about later. Yeah, so that's basically the end of the technical part. And let's go, oh, sorry, one last slide. So here's a comparison of different persistent snapshotting approaches. So so we are proposing an approach that has low synchronization latency and low memory overhead, but extremely complicated to implement. And so I think this is still better compared to messaging and also shared memory with duplicate states. Yeah. Okay. So let's talk about the implications. So these are some scenarios that I think this re-architecting will benefit the most. So first one is progressive page loading. So for example, one benchmark that we have been using to test rendering performance is the 1-page HTML spec, which is a really, really long page without JavaScript at all. And in this scenario, we will have the business thread that keeps parsing and building the DOM tree, and another rendering thread that keeps rendering it. And the 2 threads should not block each other at all. And another scenario is when we have frequent user interactions. So right now we have rough aligned input events which run on the main thread. And those input events actually need to do a forced style and layout update, which isn't great, especially if the event handlers update the layout. So with this change, what we can do is we trigger the UI events on the rendering thread, do all the heat testing there without doing any layout. And then if there is any need of, for example, JavaScript event handler, we post another task in the main thread, or I mean business thread. And finally, it's about CSS animations. So because with this proposal, we can do rendering completely on the rendering thread without involving the main thread at all. So what we can achieve here is we can run CSS and animations. I mean, all kinds of CSS animations without involving the main thread at all. So so this is like how we currently can do composited animation on the CC thread while the main thread is running JavaScript. But that only applies to composited animations like transforms, clipping, and those kind of things. And here, this is widened to all kinds of CSS animations because since we just need to recalc style and layout based on the timeline, and as long as the DOM doesn't change, we can do that. I don't know how useful this is, but it sounds cool. Okay, now let's talk about the less good scenarios. So earlier I said in the abstraction that I consider rendering as just consumers of the page state. But it's not exactly that. For example, again, animations. So if the CSS contains animations, it will actually create animation state, and which we still need to think about as part of the page state. So maybe we need to host that animation state on the rendering thread instead of the main thread. So we need to, yeah, so, and we consider that as part of the rendering output and let the rendering thread update it on its own and pass it to the main thread. And also, CSS may trigger resource loading, like triggering image loading and font loading and these kinds of things. So so here, which means the resources also need to be version labeled. So for example, if we are rendering a historical version, at which time the resource hasn't started loading or is still loading, then we shouldn't put it into our render output. So the page state is not just a persistent DOM tree, but it will include a bunch of other stuff. But I believe it's going to be simpler than the DOM tree. Well, the DOM tree is still the most complicated part of it. And finally, the worst part. So first of all, JavaScript. Again, JavaScript. So there are a number of JavaScript API that will force a synchronized layout update. For example, oh, sorry, a different order. So the JavaScript API that needs to be currently they're specified to run at a specific stage of the render update. For example, request animation frame and scroll event, they are required to run at the beginning of a frame update. And also we have resize observer, which must be run exactly after layout, before paint, and it can trigger a relayout. So if we want to strictly follow the spec, then there's nothing much we can do other than we just block and wait, which isn't great. So so we can like propose alternatives. So for example, we use animation worklet instead of request animation frame, because with a limited context, we can actually run it on the render thread. And also we can replace those synchronous event listeners with async observers. Or if we want to deviate a bit from the spec, for example, we trigger request animation frame. So it's like if we want to run RAF, we just make it a task that's triggered by the rendering thread, but we don't care about if it's changed will be immediately shown in the next frame output. So, but we don't. I don't know how much it will break the web compatibility. Yeah, and another type is those that can force style layout, like offset left, element point, get computed style. Again, there's not much you can do other than blocking, which is bad. So and if we change this behavior of this API, is going to be even worse. So maybe the only way out is we introduce asynchronous alternatives and ask them to use these asynchronous observers instead of synchronous functions. But anyway, so we already know that these APIs are not good. So if so, here is just another reason to make them even worse. So yeah. And finally, long JavaScript tasks. Yeah, so this is the worst of the worst cases because if JavaScript is running too long, there's not really much we can do. But at least the page still animates. We can run all kinds of CSS animations while the main thread is blocked by JavaScript. Yeah, and there are other opportunities if we can achieve what we described before. Like, so first of all, we can make the rendering pipeline parallel. So since we can, for example, maybe we can parallelize the style recalc, which has been discussed before on Blink Dev, or parallel layout like how server is doing, or parallel text shaping, or we can make layout and paint parallel, etc., etc. There's a lot of there are a lot of ideas that have been proposed previously, but none of them have been implemented because we don't have a parallel rendering pipeline at all. And this is actually a general idea that is not specific to Blink. So if you think about it, the basic model is, so on the same thread you have mutator tasks and consumer tasks, and there's a shared state. So as long as it satisfies this modeling, and then we can break it into two threads with the technique. So so one typical scenario is like we might apply it in the UI updates in other applications like operating system or even I'm thinking about gaming because so once I play some game with mod scripts and the mod scripts are running so long and the game completely freezes, which isn't a good experience. Also, we might apply it to the current Blink pipeline between main and CC, or the commit step, or just anywhere between two stages of a pipeline. Yeah. So finally, if we really want to implement it, this is a very rough roadmap with a lot of details missing. So first of all, we need to make all pans support cross-thread traversal. So so currently, so this it's like if we have a member on one thread and we want to another thread want to create a cross-thread persistent of that object, is actually not thread safe because the when we are running this assignment operation, it's not atomic. so garbage collection can be triggered in between. So it's like we obtain the value of that pointer, and then garbage collection is run, and then we assign that pointer to our persistent, and this persistent becomes a dangling pointer, which is. And so we need to make it thread safe, and then and also we need to break all the direct references between DOM and the render objects like layout objects. So we need to, because these will be in different threads, and we don't want to create a Meulian cross-thread persistent between them. So they should be replaced with IDs, and then we fatten all the DOM nodes. And also we might introduce something like persistent container classes, like persistent vectors, persistent hash tables, because we don't want to like copy on write an entire hash table, which sounds bad. Yeah, and finally we move the render objects and begin mainframe to another thread, and then add blocking and blah blah blah. And yeah, and I'm wondering if we can just start a prototype, not on the trunk, because I don't see how to make progress there. It's really complicated. So maybe we can do some prototyping on a separate branch. Yep, that's it. So any questions?
Let's see.
Hi. I have a-
Yep, go ahead.
So is there a prototype, a proof of concept at all?
Yes, there is a prototype. So so here at Huawei, we made a prototype that runs.
Right, so is that published somewhere?
It's not published yet. So yeah.
Hi, John Ross with. Yeah, so question for you. Looking into this, did you measure how much of the current mainframe to commit is being spent on business logic before compared to being spent on the actual layout and style to get confirmations of if the business logic is what's making us miss all the deadlines?
I haven't done a lot of performance studies yet.
Okay, thanks.
Mason on the chat.
That may have just answered my question. Firstly, awesome presentation. I'm curious to see new stuff as you're working on it. So performance is kind of the key question here in the whole thing. So like the first thing that would be great to see is performance numbers, because while I think, separating the two, I think is obviously going to be a good speed up. There's a lot of overhead, it sounds like, in your approach, right? Making fat nodes out of everything and having to use handles to connect between DOM nodes and layout nodes and things like that. So it'll be really great to see like just a rough prototype, whether you can get speed improvements.
Yes. So right now, this proof of concept is really too simple for any performance study. So it's just a correctness verification. So to get some performance numbers, I think there are still some longer way to go. Yeah.
Still very cool. Thanks.
Michael in the chat.
Yeah, thanks. Can you hear me?
Yes.
Okay, perfect. So to follow up on John Ross's question, and I think Mason's point, we do see quite a bit of like style and layout impacting performance. And while JavaScript and long tasks were hinted at as like the biggest single source, as we drive those down, as we land scheduling primitives and we motivate developers through APIs like long animation frames, we see those reduce down and we see frame rates go up on main thread. And so the relative proportion of time spent in rendering stages goes up and up and up. So the relative overhead goes up and up and up. And some of the things that were hinted at in this talk, like hit testing for events, and then those events applying style updates, which then cause more layout for future events, comes up in tracing. So I don't have specific feedback about the parallelization. I don't know how viable that is. I think it's very interesting and good proposal. But even just decoupling that part of it, like events and hit testing, and like the browser does layout thrashing without any JavaScript at all today on style and layout. And as pages get bigger and more complicated, we're already doing a lot of that work. And I think some of these data structures could help with those problems, is my thoughts. So there's a lot of opportunity here, I think.
Okay, thank you.
And Robert from the chat, are you still hands up?
Yep. Yeah, I left a comment in the chat, but I wanted to add a little bit more context. You mentioned like pushing developers to use asynchronous APIs or possibly breaking some of the assumptions of how current APIs work. I think a more tractable path is to think of this as similar to compositing more effects, where it is already the case where if you run RAF and you're too slow to produce a frame, we will happily render the next compositor frame without the input of your JavaScript. And so we could do the same thing for the mainframe production, where if your business logic does not complete within some deadline, we don't include those DOM changes in the current frame, and we happily render what would have happened absent any business logic. And then this is just as if we had composited that effect. And I think this will extend nicely to all of the current like problem areas that you identified with JavaScript and needing to interact with the page state.
Yeah, thanks. So one difference with compositing is here the change might be web visible. So yeah, so for example, if you so let's say we have a RAF at the beginning of a frame and say intersection observers at the end of a frame. So so right now you should expect what we do in RAF immediately observable in intersection observers. Yeah, so this might break something. So I'm not sure.
We could
I'm not
still
sure how serious that will be.
We could still provide that guarantee if it was necessary by delaying the intersection observer to be the result of the frame produced by your RAF. So we wouldn't actually update the intersection observer for the intermediate fake frame until we had updated the DOM based on your RAF mutations. And then we would preserve the assumptions about intersection observer following RAF.
Okay. Yeah, thanks.
We have another question from the audience.
Yeah, I had a couple of questions. One of them, just following up on Mason's question about the overhead. I think that you had a couple of approaches to reduce the overhead as well. Is that, you know, you did mention that it is a smaller demo, so I was wondering if you could extrapolate on how that would translate to just the more real world use cases. The second question was going to be about the concurrency checker. You mentioned that, like, I'm curious if there are other concurrency checkers that you've kind of run this demo against. I'm mostly asking because you had mentioned, like, you can trigger a GC like in between the time where you're copying state, but there are other cases where I can think of that happening even during setup or teardown, or, you know, just kind of in between states where if you trigger that GC, it might not, you know, you might end up in a bad state where you have different copies that are not reflective of the actual state. So I'm just kind of curious about those two things.
So first, regarding concurrency checkers, so I think there are a lot of concurrency checkers. So for example, this vSyncer I linked here, it's available on GitHub. So you can try and write a small concurrency demo and run it against. And the second part is, can we apply concurrency trackers to, I think, is it about applying it to larger projects?
Yeah, I mean, larger projects too. Like, maybe I'm just looking to get a sense for, like, if sometimes when you do have a smaller demo project, the concurrency checker doesn't always catch something unless you're stress testing or you have several other threads. So I'm kind of like, I think like TSAN or CPVMem or other things, there are like tools I'm more familiar with. So I was just kind of curious about the choice of concurrency checkers as well.
Okay, so so actually at Huawei we do have done a lot of work on concurrency tracking, and we have cause some bugs in Harmony OS, which is our own operating system. So I think that indicates that these checkers actually apply to large scale projects. I think that does it answer your question?
You can always follow up offline. Thank you.
Okay, thank you.
I think that's about all the time for questions. Thank you.
Okay, thank you.